Hi everyone, I am Mark Peter Panong from BSME3A, and for today's video, we're going to talk about the deflection of the beam. But before that, let's recall that beams are used to carry loads in a whole range of different structures, and it is important for engineers to be able to predict how much a beam will deflect when loads are applied to it. Allow a beam to deflect too much and it can cause more damage to other parts of the structure, feel unsafe to the user, or fail to meet the intended function, even if stresses in the beam are too low and there are no risk of failure. Construction codes typically define what the maximum allowable deflection is, and so it's up to engineers to figure out how much the beam will deflect. There are quite a few different approaches that can be used to do this. There are 5 more common methods. All of these methods make the same important assumption, which is that deflections are small and stresses remain in the elastic region. For this reason, the deformed shape of the beam is called the elastic curve. We can define x as the distance along the axis of the undeformed beam and y as the vertical deflection of the beam. The objective is to figure out how y varies along the length of the beam. We will assume that there's no displacement along the x-axis. We're also interested in the angle of rotation of the beam, theta. Let's take a closer look at the angle. We can define the slope of the beam as dy divided by dx. Since we're limiting ourselves to the scenarios where deflections are small, we can apply the small angle approximation, and so we can assume that the angle of rotation is equal to the slope of the beam. In other words, the angle of rotation is equal to the first derivative of y with respect to x. We can start thinking about how beams deflect under load by reviewing the moment curvature equation. It allows us to calculate the curvature of a beam for a given bending moment. M is the bending moment, R is the radius of the curvature of the deformed shape, and EI is the flexural rigidity of the beam, which defines how much the beam will resist bending due to the stiffness of its material and due to its cross-sectional shape. The term 1 over r is the curvature of the beam. The moment curvature equation is the first step toward being able to calculate deflection of the beam, since it gives us information about how the beam will deform for an applied bending moment. It turns out that there's a mathematical equation that can be used to calculate the curvature at any point along a curve. We can combine it with the moment curvature equation to get an expression that relates the deflection of the beam and the bending moment along it. This equation is still quite complicated, so let's try to simplify it. Since we're limiting ourselves to the elastic deformation and assuming that the slope of elastic curve is small, the dy over dx term will be small. And since it's squared, it will be even smaller. This gives us a much simpler differential equation defining deflection of the beam. All we need to do is to get an expression for the deflection along the beam, and it is integrated in equation for twice. This is called the double integration method. It's easiest to understand how the method works using an example. That is why for problem 9.1 from the book Mechanics of Material, 4th edition by Beer and Johnston, for the loading shown, we're going to determine A, the equation for the elastic curve for the cantilever beam AB, B, the deflection at the free end, and C, the slope at the free end. Since there is no displacement and we're only going to find the 3 equations from our problem, so the first step that we're going to do is to draw the free body diagram of the cantilever beam. The second step is to apply the equilibrium equations to find the reactions at the fixed end. We need to consider the equilibrium of forces along the horizontal directions, which gives us the summation of f of x, or the forces with respect to the horizontal direction is equal to 0, which gives us the force A with respect to x is equal to 0. On the other hand, we need also to consider the equilibrium forces along the vertical direction, which gives us the summation of f of y, which is equal to 0, and which gives us the force A with respect to y is equal to P, which is the applied force. Also, we need to take the moment about A. We have summation of moment about A is equal to 0, which gives us MA, or the moment about A, minus P, or the applied force, and L is the length of the cantilever beam, is equal to 0. Transpose, and we have MA is equal to PL. Third step is to consider a portion right to the section x to x of length x measured from end point A, or the L minus x measured from the end B. Also, we need to take the moments about the section x to x. So we have the summation of moment about the section x to x is equal to 0. We have negative m minus p times the quantity of L minus x is equal to 0. Use transposition method. We have m is equal to negative p times the quantity of L minus x. Simplify. We have m is equal to px minus pl. So the fourth step is to write the general elastic curve equation. It is EI, then the second derivative of y with respect to x is equal to m. Here, the flexural rigidity is the EI and the bending moment is m. So we need to substitute px minus pl for m. Then the equation will become EI, then the second derivative of y with respect to x is equal to px minus pl. Then we need to integrate the equation to find the slope. So the right side of the equation will become px squared over 2 minus plx plus the constant c1. Don't forget to put constant or c1 in our equation when we are integrating. So this equation will become our first equation, or equation 1. Furthermore, we need to integrate the above equation, or the equation 1, to find the deflection. So the right side of the equation will become px cubed over 6 minus plx squared over 2 plus c1x plus c2. And this equation will become our equation 2. So the fifth step is to apply the boundary conditions to determine the constants. So when the x is equal to 0 and the first derivative of y with respect to x is equal to 0, with respect to the equation 1, the c1 or the constant 1 is equal to 0. On the other hand, when the x is at 0 and y is equal to 0, and from the equation 2, the c2 or the constant 2 will become also is 0. So the sixth step is we're going to substitute for 0 for c1 in equation 1 and determine the equation of the slope. So from equation 1, we have EI, then the first derivative of y with respect to x is equal to px squared over 2 minus plx plus c1. So we're going to substitute 0 for c1, then isolate the dy over dx, and the equation will become dy over dx is equal to px over 2ei times the quantity of 2L minus x. So this equation will be our equation 3. Also, we're going to substitute 0 for C2 and 0 for C1 in equation 2 in order to find the equation for deflection. So the equation 2 is ELY is equal to px cubed over 6 minus plx squared over 2 plus c1x plus c2. Substitute, and we're going to isolate the y, and the equation will become y is equal to negative px squared over 6ei times the quantity of 3l minus x, and this equation will become our equation 4. Therefore, the equation of the elastic curve for the cantilever beam point AB is y is equal to negative px squared over 6ei times the quantity of 3l minus x. The seventh step is B, to calculate the deflection at the free end of the beam. So we're going to substitute L for x in equation 4 and then simplify, and in the equation will become y is equal to negative PL cubed over 2EL. Since the equation is negative, therefore the deflection will be in the downward direction. Therefore, the deflection at the free end of the beam is y is equal to PL cubed over 2EL in the downward direction. And the last step is C, to calculate the slope at the free end of the beam. So from the equation 3, we're going to substitute theta for dy over dx and L for x in equation 3. We're going to substitute and then simplify, and the equation will become theta is equal to PL squared over 2EL in a clockwise direction. Therefore, the slope at the free end of the beam is theta is equal to PL squared over 2EI in a clockwise direction. That would be all. Thank you for watching.